Hello everyone, and welcome to Unit 5. This is going to be Chapter 5.1. We're going to introduce our trig identities unit. We're going to first go through some of the trig identities we already know. Some of them we've already seen either in this class or in past classes. And then we're going to introduce a few new ones, and we're going to demonstrate, I will demonstrate how we're going to work through these specific type of problems, a little bit different format than what we've seen in the past. So we're going to start with some things we already know. We know about our reciprocal properties. We know that tangent and cotangent are reciprocals of one another, sine and cosecant, and cosine and secant. What this means is that I can directly replace any of these functions with their reciprocals. So if I have 1 over tangent x somewhere, in a simplify problem or a verify problem, I can directly replace it with cotangent. So we'll leave that there for now. The other known properties we use on the unit circle. We know that tangent x is the same as sine over cosine. And using this idea of reciprocals, we know that the reciprocal of tangent is going to be the reciprocal, as you can see here, cosine over sine. So these quotient properties are also valuable. The real utility of them is they allow us to move between tangent and cotangent back to sine and cosine, where we're usually more comfortable. Next, we have our odd and even functions. We know that cosine and secant are even. And we know that sine, cosecant, tangent, and cotangent are all odd functions. We don't use these quite as much in our proofs and our identities, but they're certainly good to have in the back of our head. It helps us deal with negative signs, basically. If I can rewrite, using, if I have cosine of negative x, I can rewrite it as cosine of x. That might be valuable as I work. So we're going to get into some identities here. I'm going to prove this first one for us and show how we can achieve the other two Pythagorean identities. They're not going to be proofs in the way that we'll talk about proofs later in the lesson, but just kind of showing how these will work. So I'm going to construct a triangle here. It's going to be a right triangle. We're going to let the horizontal component be x, the vertical component y, and our hypotenuse r. Additionally, we're going to label one of our angles with theta. So, as you might expect with a Pythagorean identity, we're going to start with our Pythagorean theorem. And with this particular triangle, that's going to look like x squared plus y squared equals r squared. Now, ultimately, we are trying to recreate this identity here, sine squared plus cosine squared equals 1, out of our current, Pythagorean theorem. So if I want to create a 1 here, what I can do is I can divide our entire equation by r squared. What this allows us to do is it gets us a little bit closer to where we want to go. I'm going to rewrite these as fractions, x over r quantity squared plus y over r quantity squared, and r squared over r squared, regardless of what r is, will equal 1. So we've gotten a little bit closer here, and then we're going to use our last bit here. We're going to use the fact that sine we know is opposite over hypotenuse, and our cosine is going to be our adjacent over our hypotenuse. Well, in this particular triangle that we've drawn, our opposite side is y, our adjacent side is x, and r is our hypotenuse. So we can actually replace this quantity here, x over r. X over r is our adjacent over our hypotenuse. In other words, this is cosine squared theta. And then we can do the same thing with our y over r. We can see here that y is our opposite side and r is our hypotenuse. So we can rewrite y over r squared as sine squared theta. and that all equals 1, and that's where we were going. So using this geometric proof and using some right triangle trig, we can see how we can move between algebraic and trigonometric identities. All right, so we're not going to prove necessarily we can turn over to the next page of our notes. We're not necessarily going to prove these, but I want to show you a method to create these identities. I always had a hard time memorizing all three of these. They just kind of jumbled together in my head. So if I know this first one, this the identity we just proved, sine squared theta plus cosine squared theta equals 1, we can use this to generate these remaining Pythagorean identities. So if I want to create this second identity where I have tangent squared plus 1 equals secant squared, I can start with our first Pythagorean identity, that's sine squared plus cosine squared over 1. And what I want to do is I want to divide all three expressions by cosine squared theta. Oh, I don't need that equal sign, excuse me. And then we can simplify each of these individually. Using my quotient property, I know that sine squared over cosine squared is really tangent squared theta. Cosine squared divided by cosine squared is 1. And using my reciprocal property, I know that 1 over cosine squared is secant squared. So just through a simple one-step process, we can generate this second trig identity. If I know sine squared plus cosine squared equals 1, all I need to do is divide by cosine squared to create this new identity. We're going to do the same thing on our third. We can again start with our favorite, sine squared plus cosine squared theta equals 1. I call this my favorite just because it's the easiest to remember. Sine and cosine are, the most common trig functions we use, and they're squared, add them together, and we get 1. As I said, they just seem a little bit easier to remember. Well, if the previous identity was achieved by dividing by cosine squared, we're going to do the same thing here and divide both sides of our equation by sine squared theta. What that will look like, sine squared over sine squared will get us 1. Cosine squared theta divided by sine squared theta, that is our quotient identity for cotangent. And then finally, 1 over sine squared, that is our reciprocal identity for cosecant squared theta. So again, these are not traditional proofs, as we'll see later in the lesson, but these are the most reliable ways to generate our more challenging Pythagorean identities from our primary sine squared plus cosine squared equals 1 identity that we are most familiar with. All right, so I've referenced these proof type problems. What are we really doing here? We'll verify, we'll talk about these strategies in a moment. Verify, they want us to use mathematical manipulation to convert one side of an equation into the other. And then when we prove things, we're going to do the same thing. We're going to verify. We're going to work on one side of our equation and turn it into the other. But when we prove, we verify and justify each step in a 2-column proof. So verify and prove, there's a lot of similar moves we're going to make there. The big difference between them is just this 2-column proof idea that we'll explore a little bit in a few moments. Simplify, I mentioned this in class today, but this is my least favorite because we don't necessarily know where we're going. When we simplify, what we're really doing is reduce an expression to its simplest form. And this definition is part of what I find frustrating as a doer of math. We don't always know where we're going, and we don't always know what that might look like. So just some examples here. Maybe our simplified form could be sine of x. Maybe our simplified form could be 0. Maybe our simplified form could be cosine theta plus 1. There's a lot of different ways our simplified form could look, but these are just a few examples. So what I really love about this chapter is what you can see here in the strategies. We'll talk about these as we look through the problems, but generally we want to simplify the more complicated side first. So there's some choices we have to make early on in the process. What does it look like when things are more complicated? Generally, the more operations, add, subtract, multiply, divide, the more complicated it'll be. Addition and subtraction tend to be more complicated than multiplication, but it's not always, an airtight case, right? It's going to differ based on the situations. As we work through these, we want to look for expressions where the Pythagorean identities can be used. Factoring and combining like terms can be helpful. Finding common denominators and writing expressions as a single fraction can be helpful. And then here, barely mathematical, but when nothing else seems like it'll work, rewrite the function in sine and cosine. It's a little bit of a fail-safe. If we're stuck, we can always do that. And then my favorite, don't give up, right? Just keep trying. You're going to hit these brick walls at times. You're going to hit these problems where you're not quite sure what it should look like or what it should be. You just got to keep trying, and practice will improve your skills here. So let's look at a few examples. We're going to look at a couple verified problems, and then a proof and a simplified problem. So just to kind of use some of the properties and some of the ideas that we just talked about, I'm going to verify. In other words, I need to turn one side of my equation into the other. I could do this. I could work on either side, but because we generally find it easier to simplify than to complicate, we want to choose the side of our equation that is more complicated. So I'm going to work on the left-hand side here, and I don't have a ton of options at this point. One option is going to be rewriting things using our quotient and reciprocal properties in terms of sine and cosine. So what that'll look like is secant x will turn into 1 over cosine x. And cotangent of x will turn into cosine of x over sine of x. Now, as I approach this, I didn't really know that this would work out so quickly, but I can already see a path forward, right? By rewriting things in terms of sine and cosine, it opens up some algebraic moves. Now, I have a fraction times a fraction here with a common factor in both the numerator and denominator. That allows me to cancel, so I can really rewrite this expression as 1 over sine x. And then all I need to do is use my reciprocal property to rewrite 1 over sine x as the cosecant of x. We have proved what we wanted to prove. We're very happy about this, and we can move on to another problem, right? We want to take systematic formulaic steps here to go through our process and simplify it as quickly as we can. Understand that your path might take an extra step or two if you went in a different direction. Let's move on to another example. Here, it's a little bit more complicated looking. And as I look at this, I'm going to work on the right-hand side. As I said earlier, generally addition and subtraction is more complicated than multiplication. So I'm going to work on the right-hand side here, and I'm really thinking about what I can do. I have two terms here that I'm eventually going to have to turn into a single term, so maybe a common denominator could be helpful. So I'm going to make a common denominator of the product of my two denominators, 1 minus sine A times 1 plus sine A. And what that'll lead to is a numerator that on the left will turn into 1 plus sine A, and on the right will turn into 1 minus sine A. Nothing special about this. Why did I choose to do this? Well, because I could. I had a fraction that was being added together. If I want to add fractions, I need a common denominator. So now I'm going to simplify my numerator and simplify my denominator. My numerator is going to be just regular old 2. At this point, I'm feeling good about that because I have a 2 in where I'm going, but just we can keep moving forward here. The sign is positive here and negative here, so they will cancel. In my denominator, if I were to distribute that pair of binomials, I will end up with 1 minus sine squared a. And hopefully that rings a bell from some of our Pythagorean identities. Now, we know that sine squared a plus cosine squared a equals 1. So if I were to subtract 1 minus subtract sine squared a from both sides, I would get the statement that cosine of a equals 1 minus sine squared a. This is simply just a manipulation of our Pythagorean identity, so I can replace 1 minus sine squared a with cosine squared a. That's helpful to me because my end result, I want to end up with 2 times secant squared of a, and a cosine in the denominator is the same as a secant in the numerator. So I can rewrite this as 2 times the secant squared of a, which was what we had set out to prove, right? We were trying to turn this into this, and we got there, right? That's our goal here. We're trying to turn one side of our equation into the other. Next, we're going to look at a proof. And again, I think it's a little bit easier to look at the right-hand side here. So I'm going to start with my first statement, cosine x over 1 minus sine x. And, in a 2-column proof, always a good habit to just write down our first step as given information. It's kind of establishing that we're going to work on that right-hand side. Now, I can see that eventually I want to create secant and tangent. So I may need a more complicated denominator. I know that secant can be written with a denominator of cosine, as can tangent. So what I'm going to do as my second step, it may come a little bit out of the blue, but I'm going to multiply by a complicated version of the number 1. I'm going to multiply my numerator and denominator by 1 plus sine of x. And what allows me to do that is what we call the multiplicative identity. Multiplicative identity tells us that when we multiply something times 1, it doesn't change its value, right? That's how we're justifying the statement that step 1 is equivalent to step 2. All right, on our next step, we're going to go ahead and distribute. So we will have cosine x plus cosine x sine x. And then in our denominator, we'll end up with 1 minus sine squared x. And again, that we justify that through the distributive property. All right, we're getting somewhere now. And my next step would be to convert that denominator. Through our Pythagorean identity, we know that 1 minus sine squared x is really the same as cosine squared x. And then I'm going to keep my numerator as is. The way we justify this is through our Pythagorean identity. So as you work through these proofs, you're going to find that they generally feel like a verify problem, right? We're following a sequential order of things, but at times we need to, not at times, the whole time we have to justify our work. We need to explain why one step is the same as the next. So the next thing I'm going to do is I'm going to kind of circle back and try to remember where I'm going. I know that my end goal here is to get secant x plus tangent x. So I need to split this fraction, all right? So I'm going to split this fraction into cosine x over cosine squared x plus cosine x sine x over cosine squared x. I like what I'm seeing here because now I have 2 terms instead of 1. I'm getting closer to where I want to be. I would justify this step. It's called fraction decomposition. If you want to write it as simplify, I think that's also reasonable, right? All we've really done is used, a basic idea of fractions. Now we're going to go ahead and simplify. We're going to divide both sides. So I'm going to have 1 over cosine x plus sine x over cosine x. This is just division. And then, oh, sorry, I misnumbered there. This should be a 6. Probably should be a little bit better at getting my numbers in order as a math teacher. Let's not worry about it. And then our last step here, we can see that we're getting close. Our 7th step, we can group these together. We can write this as secant x plus tangent x. Just be careful. If we want to group these together, I'm honestly doing it because I'm running out of space here, but I need to justify each of those steps individually. It is both the quotient and the reciprocal properties, or identities, that allow us to justify. So 2-column proof, right? It's a justify problem on the left. It's a verify problem on the left, and then we justify each step on the right. Thanks for hanging in there, team. We got one more problem we're going to look at here. We're going to work through a simplify. In this particular problem, we have sine x times tangent x plus cosine x. Not sure where we're going to go, so I'm going to figure, well, I can rewrite tangent x. I can rewrite this as sine x times sine x over cosine x plus cosine x. So what moves can I make here? I can multiply on the right. On the left. I can write the numerator as sine squared x over cosine x. But I also want to try to combine this with this cosine x. So I'm going to get a common denominator. I'm going to rewrite this as cosine squared x over cosine x. And what that allows me to do is I can see that in my numerator, I have sine squared x plus cosine squared x. That's one of my Pythagorean identities, our favorite one. So this fraction here can be rewritten as 1 over cosine x, which we know through the reciprocal property is the same as the secant of x. And we are done. Nice work, everybody. Remember, the big idea in this lesson is to keep trying, right? So take a look at those practice problems. My answer key is posted as well. Make sure you're attempting everything. Don't get frustrated and do your best. Thanks, everybody.